Hi guys, hope you're well, coping with coronavirus and enjoying the weather. I thought, seeing as we can't go sailing, I'd do a little bit of thinking about sailing instead, and in particular, I was thinking about a question my son asked, which was, if sheeting in helps us point higher, why don't we sheet in all the way to the centreline? I thought that was a really good question, and I didn't have a great answer for him, apart from because it's not very fast. But as you can see in this video, actually the A-class cat does pretty much. So that led to another question. What is the optimum sheeting angle? And here I'm going to try and answer that. So if we take a solo in some wind and we sheet in, so in this example there's a 10 knot wind and the boat is pointing at 41 degrees to it, and the boat is sheeted in to the middle of the side tank, which is 8 degrees. Turns out that the inside edge of the side tank is about 6 degrees and the outside edge is about 10 degrees. If we assume the boat sailing at 5 knots, which is about right, maybe a touch fast, maybe 4.7 is a bit more realistic, and if we assume the leeway angle is 4 degrees, then we can produce a speed triangle to work out what the apparent wind is. We can either measure that or use the cosine rule to calculate it, and it works out to about 14 knots in this case. And similarly, we can either measure or calculate via the sine rule beta, which is the apparent wind angle, and in this case that works out to about 30 degrees. As the apparent wind flows over the sail at an angle of attack, alpha, where alpha here is just under or just over 18 degrees because it's the apparent wind angle minus the leeway angle minus the sheeting angle, that produces a force which I've labelled here RA, and it is convenient to split that force into two components, lift and drag, and there are various formulae or textbooks that will indicate what a typical lift coefficient is, and in fact there's been wind tunnel tests on fins and lasers, and a coefficient of lift of somewhere between 1.2 and 1.4 is pretty typical when we're at those kind of angles of attack, and the lift to drag ratio is somewhere between 4 and 5, so I've assumed here it's 5. That lift to drag ratio, as we'll see in a moment, is really critical to the performance of the boat. So the angle between the lift and the total force is called the drag angle, the aerodynamic drag angle, and it is really just the cotan of the lift to drag ratio. Now the boat will accelerate forwards and sideways until there's an equal and opposite reaction produced by the hull and the centreboard and the rudder, and that itself can be split into lift and drag components, where here the drag is in the direction of the boat, so the leeway angle essentially, and lift again is at right angles to that. And if you look carefully you can see a small amount of green drag, which is the drag of the centreboard, and the orange drag is the drag of the hull. And I've done some checks and that comes out to about 70 newtons, which ties in pretty well with tests done on lasers and bites and tasers and canoes. So it's about the right sort of ballpark. And from this we get another drag angle, the hydrodynamic drag angle. So what? So it turns out if we add together the aerodynamic and hydrodynamic drag angles, they equal beta, our apparent wind angle, which is itself made up of the angle of attack, the sheeting angle, and the leeway angle. And there's proof in this case, both came out to 30.4 degrees. So just to reiterate that, the sum of the aerodynamic and hydrodynamic drag angles is our apparent wind angle, which is itself set by the angle of attack, the sheeting angle, and the leeway angle. So what, you're thinking? Well, turns out that if we can minimise beta, we will go best upwind. And I'm going to try and show that here now. So here's the speed triangle again, where the true wind is coming from the north, the boat is sailing upwind on port tack, and the apparent wind is shown by the pink line. Now, our speed upwind, our velocity made good, is the yellow line here, and it's actually just the cosine of the boat's angle to the true wind, gamma, and beta is again the apparent wind angle. The angle at the top then is the difference between gamma and beta, so that's the amount that the apparent wind is shifted by the boat's motion. And from this we can get a number of identities, so sorry, this is a bit like school, but the ratio of the VMG to x is the cotan of gamma, the ratio of VMG plus VT over x is the cotan of gamma minus beta, and from that we can get that the true wind is the cotan of gamma minus beta minus the cotan of gamma, which is a big mouthful, but it leads to this important relationship, that the ratio of VMG to VT, which clearly you want to maximise, you want the best speed towards the wind that you can get, is given by this identity here. So we're looking to maximise that ratio for best windward performance. And if we plot a graph of that line, like this, we can see that we get highest VMG when the beta is smallest. That's really crucial. So what that says is best upwind speed when beta is small. Beta is small when the lift to drag ratios of the rig and the hull and the centreboard are high. We want lots of lift, very little drag. It's not about maximising lift, it's not about minimising drag, it's about getting the best ratio between lift and drag. And I'll try to demonstrate that here. If we were to take our solo, sheet into the centre line and head up, so effectively rotate the hull underneath the boat, underneath the rig, and if we assume for now that the boat speed is the same, we can again plot the apparent wind direction and speed, and we can compare it to the apparent wind as it was before. And we can see, if we want to maintain beta the same, boat's going to have to make more leeway. And in fact, in this case, it's now making nearly 10 degrees of leeway. Now, it's kind of intuitive that the more sideways the boat is sailing, the more drag it will have. It will also have more lift, of course, so that isn't necessarily obvious that the lift to drag ratio is worse as a case. But if we look at this, if we imagine a boat that makes no leeway, produces no side force, but it does have resistance. And as we increase the leeway slightly, the resistance will go up slightly and the side force will go up slightly. As we increase the side force further, the resistance will go up too. But resistance always goes up faster than side force because drag is related to the lift squared. And so there will be an angle. Here I've assumed 4 degrees, which is the optimum leeway angle for the best lift to drag ratio. And what that means is we always want to be sailing at that optimal leeway angle to get the best hydrodynamic drag angle, to get the smallest beta. So, in the example I've just shown, the aerodynamic drag angle is the same as before because the angle of attack to the wind was unchanged. The hydrodynamic drag angle must be bigger because drag grows faster than lift because drag is related to lift squared. Therefore, beta is bigger and therefore VMG is smaller. To summarise all of that, the sheeting angle, the optimum sheeting angle, is the angle that gives us our optimal leeway angle. So we actually use sheeting angle to control the leeway angle to get the best VMG. That's it. Thanks very much. Cheers.
Bye.